Today my topic is Can pre-class GitHub contribution predict success by student teams? This is the first step of our systematic study about how to use student pre-class GitHub knowledge to benefit both educators and students. I'm going to overview the importance of this study, then introduce some necessary background as well as the methodologies we used in our study. After that, I'm going to present our results and discuss them. I will also talk about the implications. I will give a short summary at the very end. Like the title suggests, why we conduct research on GitHub data, there are several reasons. GitHub is heavily used in the education industry. It is constantly growing in number of users and projects. You can see a lot of supportive data on these slides and also on the internet. Another very important reason is because it is very mature now. This graph shows the Google Scholar mentions from 2010 to 2021. The research interests keep growing in the first 10 years after GitHub's launch in 2008, but keep dropping after 2018 as GitHub was arguably fully adopted and the research interest declined. Two research questions are studied in this paper. Question 1 is the success of student teams better predicted by the maximum contribution of any team member or by the average contribution of all team members? Question 2 is which pre-class GitHub contribution lead to the success of student team projects? Okay, let's introduce some necessary backgrounds. First, our data source, which is a software engineering class that has been taught here at NC State University for over 15 years. This class focuses on object-oriented design and development with language Ruby and the framework Ruby on Rails. The class is a semester-long class. Students will learn programming language Ruby in the first month, finish a small full-stack app in the second month, working on an open source software project in team of three in the third month. Topics including refactoring, writing tests, and fixing sets of related bugs in the current codebase. In the last month, students work on final projects in team of 3 or 4 and apply the design knowledge they have acquired in this class to add features to the current system or update a large piece of functionality. The class has been taught by the same instructor throughout the past 15 years. Class projects are based on NSF-funded project originated by the instructor. Each team is required to submit a pull request against the original repository. Projects are graded based on the quality from a software engineering perspective. Our study is based on the 2 open source software projects done by students in the last 2 months of this class. We collected all project submissions from 2011 to 2021. Most of the submissions over the past 10 years are pull requests. Others are repositories. We checked who were the participants in every pull request and users in the repository's commit history that manually located their GitHub accounts. We matched the GitHub accounts up with specific students based on their GitHub profiles and class roster. We look up the missing students' GitHub accounts with their personal information, such as name and email addresses. About 5% of all the GitHub accounts we retrieved from the past 10 years belong to this category. Overall, we successfully retrieved 1,081 GitHub accounts from 1,253 students who have taken the class from 2011 to 2021. Here is a table of the number of students, number of GitHub accounts collected, and the retrieval rate of every semester since fall 2011. We can observe a more stable and better retrieval rate start from 2016. For all the accounts we collected, we developed the scripts to query all the publicly available user information that GitHub logged from account creation date to August 2021. For every metric we logged, GitHub provided a specific timestamp for when this object is created. We then searched the school calendar from 2011 to 2021 to retrieve the exact date of the semester start and end for every semester. We also retrieved the students' open source software team projects grades for the past 10 years as the classification label in this study. This table shows all metrics we logged from GitHub and their explanation. The metrics in the red box are traditional software engineering metrics. For example, commit contribution is the number of commits the user made. Pull request contribution is the number of pull requests the user opened. For most of them, their name explains where they are. The metric in the yellow box are the number of different type of comments a user created on GitHub. The metrics in the green box are metrics related to user repositories. The details are in our paper. For repositories, we divided the repository into 4 tabs that is represented by the X in this table. I will introduce this in the next slide. We divide repositories into tab A, B, C, and D based on whether the repository is forked or not, and whether the student is the owner or collaborator on the repository. For example, tab A is not forked, and the student is the owner of the repository. Tab D is forked, and the student is the collaborator on the repository. We want to see which type of repository can better reflect the student technical ability. We think that a Type A repo is the original repo and created by a student. It should play a different role compared to a Type D repo that is forked by the student and the student's collaborator on it. Besides that, we also sample the top 10 popular languages on GitHub to recalculate the repo size for each student, as we think these languages are closer to full stack development, so they should matter more than other languages in software engineering class. We further summarized all metrics into 3 different data sets based on the semester's started and ended days. The before size contains the numerical value of each metric before the class started for each student's GitHub account. The during side contains the metrics value of each metric during class period for each student of the GitHub account. The after set contains the numerical value for each metric after the class ended for each student's GitHub account. In this study, only before set is used for analysis. Now let's talk about data processing. The first thing we do is we further filter out all semesters before spring 2016 in our study. The reason is that only 35% of students had their personal GitHub account created before they took the class for semesters earlier than spring 2016. For semesters after and including spring 2016, we have 69% of students had their GitHub account created before they took the class, which is almost the double of the percentage before 2016. As shown in the table, so the data starting from spring 2016 is more meaningful to our research. Our final dataset includes the total of 768 unique students, from among whom 714 unique GitHub accounts are retrieved. The retrieval rate is 93%. These 768 individuals formed 421 unique teams. Each student was on 2 unique teams, one for the first OSS project and the other ones for the final projects. For those 7% of students for whom we have no way to retrieve a GitHub account, we treat them as if they did not have a GitHub account before the class. This means we fill in zeros for all metrics for those missing accounts. For repository size metrics, we reported the log of list 12 features since their value are too large compared to other features used in our study. This concludes how we manipulate the raw data. Since we want to discuss a team instead of individual performance in this study, we model our teams in 2 ways with the raw data we collected. We took the average of each GitHub contribution metric we collected across all team members to model the average technical ability of a team. We also took the maximum of each GitHub contribution metric across all team members to model the maximum technical ability of a team. We then divided the 421 teams from 2016 to 2021 into three groups based on the grade they received for their projects. The top contained the top one-third across the 6 years, the middle contained the medium one-third across the 6 years, and the bottom contained the bottom one-third across the 6 years. We then constructed a six binary logistic regression model to classify top and middle, middle and bottom, and top and bottom. We choose logistic regression as our model method because has fewer assumptions and does not require normalization. We eschew normalizing our feature on purpose since we want to keep their original physical meaning when we interpreting the odds ratio. After feeding the sixth logistic regression model, we conducted traditional stepwise model selection with the ASC score as a criterion for selecting the best model with the least number of features. We conducted an ANOVA analysis to compare the model with all features used and the best model selected by the ASC score. We computed the prediction accuracy under the default threshold for all models. We select the best team modeling method based on the prediction accuracy. We calculated the p-value and 95% confidence interval and odds ratio for each feature that is used in each model. We also gave a further interpretation of the physical meaning of the odds ratio. Now let's talk about the results. Here is the prediction results of our logistic regression model. We use model prediction accuracy to select the best model for predicting top and middle, middle and bottom, and top and bottom. We can see that using the maximum to model a team works slightly better when we try to predict whether a team falls in the top or middle. However, when we try to predict the top and bottom, middle and bottom, average works better. This table shows the finally selected features in the best model for predicting middle and bottom. The features that are marked in yellow have p-value smaller than 0.05 and odds ratio greater than 1. Those are the features that are statistically significant and have positive contribution for a team to be a middle team when compared to a bottom team. For the odds ratio, simply speaking, if one feature has odds ratio greater than 1, then increasing in the numerical value of this feature will increase the possibility of the prediction results to be success. Will success in this case means middle level team instead of a bottom level team. That is why we focus on features that with odds ratio greater than 1. I will give an example interpretation of odds ratio here. For our example, the estimate for the odds ratio for every unit increase in public commit contribution is 1.02. Assuming all other metrics remain unchanged, this means an increase of one commit contribution multiplies the odds of a team being a middle level instead of a bottom level by 1.02. Similarly, an increase of one forked repository replies the odds of a team being a middle level instead of a bottom level by 3.53. This result suggests that if a member of a team on average made more contributions on GitHub, forked more repositories in full-stack development related languages, and had written more code in language used in the class, then this team has a better chance to be a middle-level team instead of a bottom-level team. Similar interpretations can be generated for the best model for predicting top and the bottom. The results suggest that if members in a team on average made more commit contributions, created more repositories, and had not only forked but also worked on full-stack development related projects before class, and contributed to a broader range of repositories, then this team have a better chance to be a top team instead of a bottom team. Last but not least, this table shows all the finally selected features in the best model for predicting top and middle. This is the model that is the hardest to interpret. The features that are significant suggest that if members in a team have collaborated on higher quality repositories and have forked a lot of repositories, then the team is more likely to be a top team instead of bottom team. This concludes the results we have. In the discussion section, we answer the research question 1 first. Is the success of student team better predicted by the maximum contribution of any team member or by the average contribution of all team members? The answer it is hard to give a universal conclusion on which method is the best. When we try to distinguish the top team from the middle teams, maximum works better. When we try to distinguish the middle from the bottom and the top from the bottom, the average gives us a better prediction power. In general, distinguishing the top and the middle teams apart is hard. We suggest that if instructor want to model student teams, then using average can help one to better distinguish the good and the medium team from bad teams. When average is not significant enough to tell two teams apart, maximum can be a good candidate to use. We believe a combination of these two can help instructor better understand the team dynamics of student teams. The answer to research question 2 is complicated. As we introduced in the results section, these are the features that distinguish each level of teams we listed in this slide. To save time, we will discuss this in the implication section. We have a detailed discussion in our paper. The implication from a student perspective are: if a team wants to improve from a bottom tier to a middle tier, they should first try to make more commits on GitHub to improve their general technical ability. Second, fork more repositories related to full stack development to have basic idea about what tasks to expect. Third, try to learn some Ruby before the class. In order to move from a bottom tier to the top tier, a student team should first try to make more commits on GitHub to improve their general technical ability. Second, get hands-on experience in the full stack development projects. And third, make contributions to a broader range of open source software projects on GitHub. When a team wants to move from a middle tier to the top tier, collaboration on high-quality open-source software projects is the key. Working with high-quality projects will teach students many real-world lessons that probably cannot be learned in the classroom. This can lead to a breakthrough from a middle tier to the top tier. From an educator perspective, we have doubts about team formation techniques that do not consider student background. We appeal to educators to think about the team formation process seriously, how to make the team formation as fair as possible with teams of even strength. From a GitHub perspective, based on the analysis results we have, we suggest that try to even out the commit number across teams can be an easy to implement solution for constructing fair teams. In summary, the main contribution of our research are: first, we mined a novel and relatively large dataset on students in software engineering class. Second, we discussed on student software engineering team modeling with GitHub metrics. And last, we gave suggestions on both students and educators about what to prepare for and what to think about a student engineering class. This concludes my talk. Thank you.